about the big omega. Oh, sorry, big O. And big O is a notation for the asymptotic function behavior. So actually, I think there are 5 or 6 notations about the asymptotic behavior or function. So the first, the big O, and the corresponding one is a small o, and there is another one, this one, and a big omega corresponding to a small omega. So there are 5 notations about uh, asymptotic behavior of a function. So let's analyze. Let's go to each one in order. So first, let's say this one. This one is a big theta, and we use a big theta when we give 2 functions fn and gn, and one n going to infinity, and for some certain there exists C1 and C2. So we can find a relationship like this. Gn is less or equal than C2Fn, and larger and equal than C1Fn, larger than 0. So yeah, the relationship is like this. Gn is between C1Fn and C2Fn. So this Fn is not only the upper bound for Gn, but also the lower bound of Gn. So that's what, if Fn and Gn have this relationship, so we call it Gn equal to big theta Fn. Actually, this is not actually the equal relationship. This actually, from the mathematically, you can understand this like it belongs to. Why? Because this is a set. This is a set. This is not a single function. This is a set. It includes many functions. So actually, you can understand this equality notation as the belong to relationship. So that's the first, the big theta. And then we go to this one, big O and small o. So for big O, we always use these 2 functions here, and it's the same. So for big O, the first one is small o, the second one is big O. And for now, when n goes to infinity, and there exists a c, this is a constant value, and we have the gn, it should be less than cfn, like that. So you can see from here, fn is the upper bound of gn. So we can get this gn equals to big O fn. Is this right? Fn is the upper bound. Yes, that's right, correct. And for example, we can have, okay, I forgot to give an example here. So for example, if gn is n, fn is also n, okay, and you can, or it is 2n, and you can find the C1, C2 here, right? Because this is n, and you can find C2 as equals to 1, and C1 equals to, I think it's 1/2. So you can get this relationship. It works, and then you can get that n equals to 2n. And if I change fn to n squared, and you still get this n equals to, yeah, from here n square, and you can set C2 equals to 1, and from this it is definitely will, yeah, for C1, okay, this is C1, and for C1, oh, yeah, you can see that you cannot find a certain C1 and to make it satisfied, so it is doesn't work. So n is not belong to n form. So when these two functions have actually for the polynomial, and you have the highest degree of this function is equal, so it will satisfy for this big theta relationship. And for this one, we give an example here. If we Gn equals to n and Fn equals to n squared, and then we will get n. Yeah, you can see that when c is equals to 1, it will satisfy this inequality. And so we can write it like this: n equals to, n squared. But when Gfn is also 2n, and can you see this work? Yeah, it can also work. We can also have the c equals to 1, and it will also work, right? Yes. So that's a big O. And for the small O, it we can write it here for the small O, and this is the inverse of the big O. So actually, for n go to infinity, and there is not, there exists. This is different for for all constant c, and it will satisfy this function for all. So that means that the limitation n goes to infinity, and Fn over Gn, it will equals to Gn over Fn. Yeah, that's right. It is will equals to 0. So Gn is small o Fn. So that means that when Gn equals to n and Fn equals to n squared, n is equals to n squared, right? But if Fn equals to 2n, it doesn't work. So that's, and the same thing, kind of similar thing happens to omega, but this is different. You switch Fn to Gn, you switch the two locations here. That means Fn less than equal than Cgn. You got the big omega relationship, and that means, yeah, get the big omega relationship, and the small omega. The relationship between big omega and small omega is the same with the big O and the small O. Okay, so this is from mathematically, and we'll see another small example from the computer science. In computer science, actually, we usually use the big O the most, and sometimes we also use the big theta. But this is for the upper bound. Because we in computer science we focus, we use this notation to represent the algorithm complexity, and we want the algorithm to run as fast as possible. So we care about the worst situation about the running time. So we care about these two the most, and sometimes we care about this, but not too much, I think. So in computer science, we analyze our algorithm. If the algorithm is like this, and 1 to n, and there will be a function here, and if this function is kind of O1, yes, kind of like something I just do a c equals to a plus b, and it will have O1 complexity because you can do it in a constant time. So constant time represent like this, big O1. And from here, we can see the total, the whole algorithm, and because it loops in time, so it has a time complexity is big O n. Actually, it is the big theta, but we use it simply, yeah, that was right. So sometimes, if we have the two loops here, we add another loop, 1 equals to n, and also and for now, we have the complexity as O(n) square. So that's why, that's how I used the big O notation in the computer science and to analyze this algorithm. And further, there may be sometimes you see like a notation like here, big O log n. Yeah, it is for some, actually the algorithm is running as a tree structure. It's kind of like running from here and running from here, and you'd go analysis here, like the running time Tn is equals to Tn plus n, like something like that. So you can do it recursively and get the data complexity like this. So if you want to know this one better, you need to see how to analyze an algorithm well. So that's all for the big N and big theta thing. Yeah, thank you.